Hey, this is Dr. B, and I'd like to give you some assistance with Module 2, Lab 1, also known as the coffee problem. You can find the details for it here at Chem Collective, and I have created a problem for you to solve, at which point, after you've solved that problem, you solve the problem given to you in the Chem Collective website. It is similar, so solving this here should help you. And also to help you further, we've done a sample problem that uses different data. So why don't we take a look at this sample data. If it makes sense to you, go ahead and solve this problem. It's similar with different numbers. And then go to the Chem Collective problem and solve that. So I thought it might help if I read through this. If you prefer just to read this on your own and make sense of it, then fine, you don't need this video, but I'm going to go through it. Here's a complete solution to a similar problem. How much milk at 5 degrees, so cold milk, must be added to 100 mils of hot tea? It's almost boiling at 98 degrees Celsius, enough to cool it all the way down to room temperature. Well, I think we're going to need a lot of cold milk to bring really hot tea down to room temperature. We'll make lots of assumptions, including any liquid, whether it's a tea or milk, will all have a density of the same as water, 1 gram per mil. And since it's mostly water, any liquid in this problem has the same specific heat, 4.184 joules per gram degree Celsius. This visual might help you. You got some hot tea, you're going to add some cold milk until it hits room temperature. Now here's how we solve it. We first begin by recognizing that the tea is hot. It's going to lose some of its heat. Where's that heat? Well, we're going to assume it's perfectly insulated and all goes to the milk. So all of the heat lost by the tea is absorbed by the milk. Heat is represented by Q. Q is in turn represented by mc delta T. Heat is equal to the mass times the specific heat times the change in temperature. So if we can get all those things, we should be able to solve for what the question is asking, how much milk, which is the mass of the milk. The key really to solving this is, see how I put a little bit of the Q for the milk and the Q for the tea? If you put those little subscripts, it helps so much or you lose track of everything. Notice what I've done here is I've just said what Q for the milk is equal to. It's equal to the mass of the milk times the specific heat of the milk times the change in temperature of the milk. Not just the temperature, the change in temperature. That would be how much warmer the milk gets. And notice that it looks like it's 20 degrees. And that's also equal to the same thing for the tea, all the heat that the tea lost, which is equal to the mass of the tea, which we'll find, the specific heat of the tea, which is 4.184, and the change in temperature of the tea. Now it started at 98 and it went down to 25, so it'll be 73. Now I'm big on rearranging everything because I think it simplifies everything, and we want to solve for this. So if I divide both sides by C milk delta T milk, it will isolate the mass of the milk. See how I did that? And there it is. It cancels on the left and it shows up on the right. Now we can plug in everything. Mass of the tea, got it. Specific heat of anything, got it. That should be a degree sign. The T got 73 degrees cooler. Notice that that's delta T, 98 to 25. I would not worry about negative sides. I'd report everything as positive because we simply need to know how much. Specific heat of the milk is the same. The milk got 20 degrees warmer, just reported as a positive value, and you'll get an answer of 365 grams. Since everything has a density of 1 gram per mil, you have to add a whopping 365 mils of milk in order to bring that tea up to room temperature. I think these are kind of cool problems. Not easy to solve, but using this as a guide should help for this and for this. All right, everybody, good luck.